started. Questions over homework?
Yes. Yes.
Okay. 63. R7. So Stephen, right? Sounds like you had a process that you tried, but your answer didn't come out to match what they had, right? Okay, so how you doing?
Go ahead and factor those two denominators out. Think about that.
So you factored the two?
Yes.
All right, so what did those factor to be?
The first one was x plus 6 times x minus 1.
That might be the problem. It should be minus 6 minus 1. Is that what you think that's it right there? Okay. Yeah, and then this one is minus 6 plus 4. And so you see they share a common factor. So that's going to help it's going to help out quite a bit. So I'll let you work back through that one. That sound fair?
I have a question also.
Uh-huh.
Number 73, I got stuck.
Same page, right?
Yes, sir.
Mm-hmm.
It's 1 over
Yeah. Okay, let's look at that one. Is it all right if Stephen, that I'm going to leave this alone? Okay. Yeah, 1 over h, and then in parentheses, 1 over x plus h minus 1 over x. Okay, so what did you do?
Well, I started trying to find a common factor from the bottom one.
You mean like in here?
Right.
To put these two together?
Right.
Okay.
I tried to work inside out.
Okay. So if you do that, if you're looking at just the inside the parentheses, then the common denominator that you could use would be what?
Yeah, that's where I got started because then it became out really, really ugly.
What do y'all think? What could I use for a common denominator here?
So no, it can't be just h because of that addition.
Yeah, because of the addition.
X parentheses x plus h.
So your LCD has to be x times x plus h, both of these factors. It can't be just x plus h.
So multiply the x plus h on one side and multiply x on the other.
I'm going to multiply x on the top and bottom here, and I'm going to multiply x plus h on the top and bottom here. That's the way to do it. And yeah, so you should have the x over x times x plus h here, then like that. Then when you put them together, be very careful with this minus sign, right? That minus sign has to distribute here and here. So you're looking at from here going to x minus h over the common denominator. And your x's cancel.
Okay, good. Okay, that's right.
Y'all see that? Minus sign goes here and here when you put those together. Now I still haven't done this part. I still have the 1 over h out here. So I come back over to this. I was just doing that on the side so I could put these in here and it wouldn't look too cluttered. So this right here becomes 1 over h times negative h over x times x plus h. And then what?
That's where
What do y'all think? Is this the same?
I'm still trying to figure out how you got the negative h on the top.
This minus has to go through the top of the parentheses, or the top, the numerator here, minus x minus h.
Like cancel out, so they don't no longer are like.
Don't what cancel out?
The x plus h on that side on the left and the x plus h on the right, they cancel each other out, don't they?
The x's do cancel, yes.
These x's do. Look, we're going to put this together, right? The numerators are going to come together. The denominators stay the same. Right, so here's your denominator, didn't change. X minus, and then this minus is to both, so minus x minus h. These two are gone. Are you saying these x's and these x plus h's go away? Don't you? Oh, okay.
I'm just being kind of dumb.
Well, I don't think so, but you got to keep asking questions. It's a good thing. Because there's probably someone here, right, who has the same question? Just maybe a little
I was
too...
doing it right. Okay. I just thought I was doing it wrong when it came out really weird, so I missed the negative.
What about this, though?
Cancel out the h.
You can take these h's because it's multiplication.
Right.
And there's still negative up top, so you're going to get negative 1 over x times x plus h. That's it right there.
That's why, okay, that's why I got it wrong.
You see it now?
Yeah.
Okay.
Because I forgot that the h has the, it's in parentheses by the negative 1, so that's why I missed that.
Okay. Okay, let's talk about today's material. Let's see, we got a pretty full class. Today we're going to talk about solving equations, 1.4. And that's about as general as you can be when, oh yeah, we're just going to do solving equations today. That's so vague, you know, that we want to talk in a little more detail about what this section is about. So the notes that I have online for you, I believe those are the ones that are up that you can print out on your own. But I'll show them to you here in class. When we're solving any equation, we must first identify the type of equation we're facing. All right, this is critical. This is critical. In my Cal 3 class, I give them a bunch of take-home exams. And on one of the problems, a student came up to me and they're like, well, I know I need to do this and this and this. And then I get to this point, and I'm like, yes, what do you do there? And they go, well, I know I have to solve this equation. I said, yes. Okay, how are you going to do that? And so part of it is recognition of how you attack different types of equations. Because the approach to attacking a linear equation is not the same as the approach to attacking a quadratic, and it's not the same as a radical equation. They're all different. And so we want to make sure going into this class that we know how to address each one. All right, so there's a list of 6 different types of equations we could be looking at. The first being linear equations, then quadratic, radical equations, rational equations, quadratic form equations, and factorable ones. We've done a few of these, right? Linear equations, and that was like a long time ago, right? Linear equations. But let's review briefly, very briefly, how it is that you would attack a linear equation. Can anyone give me a hint, set of steps, something on how to attack a linear equation? Or even just give me an example of a linear equation so we know what the hell we're looking at.
mx plus b.
Mx plus b
Y.
equals y. Because so we need an equals in here, don't we?
Right.
Okay, we have to have an equals or it's not an equation. So linear equations are equations that involve linear variables. What do we mean by the variable is linear? It's raised to the first power is what we mean. Okay? Anytime we have equations where the variable or variables that appear in the equation are raised to the first power, it is a linear equation. This is what we call a linear equation in one variable, meaning that it's an equation, there's one variable, and it's linear. Linear equation, one variable. There's another type of linear equation that you may have seen. I know you've seen. That's a linear equation in two variables. This has a solution, doesn't it? X equals something will solve this equation. This has a solution?
It's,
Can be found.
well, it's graphical.
That's right, it's a line, right? What does that line represent? What does every dot on that line represent?
It's a point.
A solution, an x and a y that make this true, right? So a linear equation in one variable should have one unique solution. A linear equation in two variables has an infinite number of solutions, right? And each solution is an ordered pair. So this is really just about like recognition. That's all I want you to see, like language, recognition, linear equation, one variable, linear equation, two variables. Now when we're dealing with the linear equation in one variable, what's the method to solve it? If you could explain it to me in layman's terms.
Solve for x.
Solve for x. Slope intercept. I think, no, we're back. I think you're thinking more lines right now. Okay, if I'm trying to solve this, solve for x, that's what I heard, right? Isolate x, isolate x. Get x by itself. So to do that, you probably do what first here? Subtract 4, divide by 3, you're done. Yes? So the main thing on linear equations, isolate the variable. Yes? Isolate the variable. I'm not going to waste your time solving that one because I hope I would be insulting your intelligence if I try and solve that for x. All right, that's linear equations. Isolate the variable. Now, what about quadratic equations? So, give me an example of one of these. Or I'll give you an example. 5x squared equals 3x plus 1. Is that a quadratic equation? Yes. It's a quadratic equation in one variable, isn't it? What if there were two variables in there? What if there was y squared in there also? You would have like a parabola or a hyperbola or something like that that you haven't even looked at yet, right?
Right.
You haven't even messed with those. We've stuck to anytime you've had x squared mixed in with another variable, y, it's been a parabola, and that's the extent of it. What we're focusing on here today, linear equation, one variable, quadratic equation, one variable. How do you go about solving a quadratic equation in one variable?
First set it equal to 0.
Okay, so it's different than this, right? That's not what you told me here. You didn't say set it equal to 0, did you? You said isolate the variable. This one, we try and get everything on one side, don't we? So you isolate 0, you could say that. You isolate 0. You get 0 by itself. Okay, there it is. And then what?
And then you would find if it's factorable.
Is it factorable, right? Is there a GCF? Like maybe there's a GCF you could pull out. What's that? The discriminant to see if the quadratic formula would work, right? If there are solutions. So you've got a couple of things in your toolbox here, right? Factoring, quadratic formula, right? How about completing the square? Did y'all do any completing the square? No, everyone always says it. No, no, no. All right. So, but we have a way, right? Okay, so we're good with this? All right, what's next? Radical. What are radical equations?
That's what the,
Square roots?
square root, there you
Yeah, square roots.
go. Right.
So I'll give you an example, and I think I'll just pull one right here out of the book. Square root x minus 1 equals x minus 7. There's a good old radical equation right there.
Correct.
So what are the steps to solving a radical equation? There's a whole set of steps. Let me see if I have them listed out here. Here we go. Radical. There we go. Isolate the most complicated radical you see. So this is a radical equation. How many radicals do you see? Just one, right? This is a radical. A radical is square root. You could have cube root. You could have fourth root. You could have fifth root. Doesn't matter. These are all radicals. So any radical equation involves a root. In this case, it's square root. So we want to isolate the most complicated radical. There, it's isolated, isn't it? What's the next thing we should do? In this case, raise both sides to whatever power will eliminate the radical. Since this is a square root, that means we'll square both sides. So I'm going to work through this one, okay? Previous two I didn't because we've done linear and quadratic before, all right? So for this one, I'm going to square both sides. And the reason we do that is what? What does it do over there to that root? Gets rid of the root, right? My thing recorded? Yes. Okay, so the radical goes away. And so what I'm left with on the left side is x minus 1. Okay. What about the right side?
That becomes more similar to that of quadratic. Maybe like x squared.
Yeah, you have to FOIL that all out, right? You have to multiply that out.
It's gonna be x squared,
A squared plus
minus
2ac
14
minus 8 squared.
Yes.
14x, plus 49.
There you go. How many of you are comfortable doing this squaring in your head? Just show of hands. Yeah. Okay, quite a few of you. All right, if you're having trouble with it, there's an easy kind of way to do it. The first term is always this squared, okay, so x squared. The last term is always this squared. Negative 7 times negative 7 is 49. So you've got the two outside ones will always be easy. The only question is what's the middle? So anyone who's doing this mentally, anyone want to tell me how you get negative 14? Go ahead.
Well, I just know that because they're by themselves, so it's going to be times those two, so it's going to be negative second x.
Yeah, you all you do is you multiply these. This and this. What's x, 1x, what's x times negative 7? So what's x times negative 7? Negative 7x times 2. Always times 2. Negative 14x. That's what goes in the middle. Stephen, you were saying the formula, right? You were like 2ab, right? So same thing.
It's a long way, that way I know I'm not messing things up.
Yeah. Okay. All right, now what?
Now you can set it equal to 0.
Why?
Because that's what we're supposed to do.
Why?
I don't know who used to solve quadratic.
That's right, because now you're right, you're right. It's a quadratic equation now, right? That's a quadratic equation now. And that's the point. The radical equation has now been converted to a quadratic equation, which we can solve, right? So we go through this process now of solving this quadratic equation. We move everything to one side. So 0 equals x squared minus 15x plus 50. We hope that it'll factor. It does. Right? X minus 5x minus 10. That work? I got lucky, didn't I? And then you set each factor to 0.
Yep, and that's going to be x equals 5, x equals 10.
X is 5 and 10. Potentially. Because for every radical equation, you must check your answers. Why do you check your answers? Because you squared both sides of the equation, right? Anytime you square both sides of an equation, you introduce the possibility of what are called extraneous solutions. That means that if you have, here's a set of numbers. If you do this process, if there are answers, they're going to be in here, okay? If there are answers, they will be in here. But you might also have other shit in here that doesn't belong here. And those may not work. And they're called extraneous solutions. So the red ones are the good, the black are the bad here, but you have to check them all to see which one is going to actually work in the original problem.
So you have to plug it back in.
You have to plug them back in to the original problem, not to the quadratic, into this, and check.
Because of course it would work.
That's right. It'll work in the quadratic because that's where they came from. So let's check them real quick. 5. What is 5 minus 1? 4 square root of 4? 2. So that's 2 equals, and then now put 5 in here. 5 minus 7? Negative 2. Uh-oh. Doesn't work. So 5 didn't work.
So then we can't have a.
So we got to chunk it, right? It's no good. Then you check 10. 10 minus 1, 9, then 3, and then 10 minus 7, 3, 3, 3. Okay? So the good news is that if there are solutions, they should be included in this set. The bad news is that you could have answers that don't work. Understand? All right. Let's take...
We need to always check for the radicals.
Yes. Mm-hmm. It can be just almost like a mental check that I just did, you know, but you need to check. If you just say these are your 2 answers, then it's
And then it's kind of up for grabs.
it's wrong. I mean, you're telling me something's going to work that's not. So I'm going to go put that, you know, I'm going to go build that bridge, right? And you're going to tell me that those are the correct specs. The bolt's going to fail. The bus of children's going to go into the freezing river. No, sorry.
That went dark real fast.
It's like, Robert,
It's just, you know, just a thought.
The moral of the story is just don't be involved in building bridges.
Check your answers. Yeah, don't build bridges. Don't build bridges.
Seems like the real moral there.
No, anytime I've ever said something like that, it usually sticks better than when I say, just you need to check your answers because I'll take off if you forget, you know. If you picture like a bus full of children going into an icy ravine, you'll probably continue to remember that the rest of this class, won't you? What about this one? So I'm giving you some examples here. What type of equation is this? Radical equation.
Could you still square both sides?
Well, yes, you could. There's nothing stopping you from squaring both sides here. You could do that.
Not even the minus?
What do you mean, not even the minus?
Well, because you can't just, or you have to square the whole thing.
You have to square the whole thing. That's the trouble with doing it now. See, if you go and try and square this whole thing right now, so I would not write this down, just watch. If you go to square this whole thing right now, both sides, then when you do this, you actually have to do FOIL. So you have to do this times itself, and that's going to be a big, ugly thing. Are you allowed to do it? Absolutely. It's just not usually the technique that we do on these. The first step is always to do what? Isolate the most complicated radical. So you want to get at least one of those radicals by themselves. The good thing about that is if you are able to isolate a radical, what's going to happen on that first squaring step? When you square it, what's going to happen? If it's a radical by itself, it'll just go away, right? The radical will go away, and that's good. The other side's going to be a mess, though. So I'm going to take one of these radicals, leave it here, take the other one to the other side. So, yeah, I think this one's good to leave. The other one, when it goes to the right side, it just becomes positive, right? So this was a negative radical. When I move it to the right side, it becomes a positive radical. So left side. Squaring both sides now? Okay, the left side's clean, right? No big deal? And I'm automatically thinking right now, I squared both sides, I'm going to be checking solutions at some point. This never ends, okay? This is always, no matter what equation you ever have, you ever square both sides, you've always got to go back and check answers. Now, it's kind of weird because if you cube both sides, you don't have the same problem. It's only when you square or fourth power or sixth power, even powers. And it has something to do with the fact that when you multiply a negative times a negative, you get positive. Positive, you know what I'm saying? The way, when you square things, that's what it has to do with. So, okay.
Good to know.
Yep. Now,
I'd kind of like to see an
square the
example
right.
of that though after this.
What's that?
I would like to see an example of what you mean though after this.
Okay. Yeah. All right, so squaring the right side, I think I'm going to do this a little slower because it's the first time we've had to do this. So this would be considered a prerequisite topic, but I understand it's been a while since some of you have actually multiplied radicals like this before. So let's talk about this first multiplication here and here. It should just go away. The root just goes away, right? Yeah. Because that's really like this times itself, right? Which is squaring it. That's the same thing. So the square root goes away. So all you get here is just x plus 2. But then you have to do this times this. So what's 2 times that radical? 2 times the radical. That's it. You just leave it, right?
Yeah.
And it's positive because it's plus here.
Yeah.
And that's a positive. So plus 2 root x plus 2. And then you do the inner one like this, which will give you what?
4 square root.
2 again, right? And then I'll put them together. I'll do it on the next line. I'll put them together. So 2 root x plus 2. Any questions?
Yeah.
Okay, and one more multiplication. 4. That one wasn't so bad, right? 2 times 2. Now the left side is what? 2x plus 3. Okay, so you step back, take a deep breath, you look at it, and you go, crap. Because what type of equation is this? It's still a radical equation, isn't it?
Yeah.
So in the steps, look at the steps I have here. Isolate the most complicated radical, raise both sides of the equation to the power which eliminates the isolated radical, repeat if needed,
So
which
you-
means you have to repeat the whole process again.
So you have to try to move everything except for those combined 4 root
That's
x
right.
plus 2.
We're going to isolate the radical again. And then just go through it again. So we're going to square both sides again eventually, but we got to get everything together. All right, so let's do it.
Oh, how fun this is.
I'm sorry?
I said, oh, how fun this is.
Yeah, I agree. All right, so this, I'm going to put those two together, right, because they're the same thing. So I'm going to have 4 of these roots on the right side. And then everything else I'm taking to the other side. This, this, and this. So what happens when I take that stuff in green, subtract them out to the other side? How many x's will I have?
1x
I'll have 2x, take away that x, so I'll have 1x,
and then -3.
and then negative 3?
Yep.
Are you all comfortable with me moving stuff around like that?
Yeah.
Because I'm hoping that you're at that point where you can move stuff without showing like vertical addition and subtraction. I mean, if you need to, that's okay, but as long as you could get to that fairly quick, this from here to there. So we're good? I can continue? All right, we have one thing we need to just kind of decide what we want to do with. The 4 in front of the root. Because it's not technically isolated yet, is it? That 4 is still there.
It's by there's a parentheses there.
Yeah, it's implied multiplication right there. I could divide both sides by 4. If I do that, keep in mind that I'm going to square both sides, right? I'm going to be squaring a fraction on the left side. So if you're comfortable with that, that's okay with me. It's a matter if you're comfortable with it. The other option would be leave the 4 there. But if you do that, you have to keep in mind that these are 2 separate factors. So it's like if I have 2 things being multiplied and I'm squaring it, right? A times B, and I'm going to square both sides. The square must apply to both, right?
So you're going to end up back to
You're going to wind up with a 16 on this piece. Y'all understand?
Yeah.
So it's your call. Remember, 2 points, different paths. I personally like to leave the 4 here. That's what I like to do. But if you want to move it, divide it by 4, it's your call. Is that all right if I just leave it like this? Okay, square both sides. So here we come. Square, square. the left side becomes x squared minus 6x plus 9. So square that x squared, square that 9. This times this, double it right there. Right side, square the 4, 16, square the square root, x plus 2. That doesn't look right, does it? What do I need there? I need a parenthesis. That's right. I need a parenthesis around there because you squared the 4. I got 16. You squared the square root of this. And now you have to multiply the 2 together. So the parenthesis must be in place. Those are those little things that you forget to do and then it throws everything off.
So why didn't you have to like FOIL that one?
Because there's multiplication between these two as opposed to subtraction between these two. And quadratic equation. So now I'm going to try and get everything to one side. I will pass the 16 through, right? And then move everything to one side. What is this? 22x minus, is that right? Oh my gosh.
Yeah, that's right.
My brain is,
Yeah, I think that's right.
Yeah. You're right.
Definitely can't factor that because 22 is a prime number.
20.
Negative 23 and 1.
Yeah, well, I think this will work.
Negative 23 and positive
Negative
1.
23, yeah, and positive 1.
Oh, yeah, you're right, you're right.
So, hey, but don't worry. We never have to worry about quadratics in terms of we always have the quadratic formula, right? I mean, like, even if you thought, hey, that won't factor, if you use quadratic formula, you should still get to the same place that we get here. It's just going to take you a little longer. So what are the two potential solutions? 23 and negative 1.
Was that back into the original?
Into the original, which was so long ago, I don't even remember what it is.
It is 2x plus 3 minus square root of x plus 2 equals 2.
All right, there it is. That's what we need to check it in, right? So shall we try 23? 2 times 23. 46 plus 3. 49. Square root of 49 is 7. Minus 23 plus 2 is 25. Square root of 5 is 2. Yes, it worked. And then plug in negative 1. 2 times negative 1 is negative 2 plus 3 is 1. Square root of 1, 1. Minus negative 1 plus 2, 1. Right? Square root of 1, 1. Equals 2? No, that's not.
So one doesn't work.
One of them doesn't work. Now, be careful. It's not always going to be the case that only one works. Sometimes they will both work. Sometimes only one works, and sometimes neither one works, and there's no solution.
What, you just put no solution?
You would just put no solution. Yep. All right, how do y'all feel about this? Y'all seem to be okay,
It's a long
but what you have to be careful with in a class like this, and I see this so many times, usually it isn't until about Cal 2 that people really understand this, is that sitting here watching me do it going, I got this. This is no problem. I understand everything he's doing up there. It's great. Class is going fine. You don't ever go do any homework. Every time you come in here, you're like, yep, I got it. Got this. This is cake. No problem. If you're not going home practicing, you're just going to get steamrolled. All right? Because watching someone do it, it's always, I know what the next step is, right? I'm not going to make the mistake of doing some weird stuff I'm not supposed to be doing. That question is, are you going to do that? You know, so you've got to work all those kinks out on your own, and there's only one way to do it, unfortunately. We're still not to the Matrix age yet, you know? You know what I'm talking about, the movie?
Yeah.
You know, we're not downloading calculus yet. just hooking up and Cal 1 got it done. That day's not here yet. So you still have to work at this to get it. So I'm only saying this because I see a few people out there that are just watching me, which is fine because I'm recording this, and I want you to pay attention to what I'm saying and understand the method. But what I get concerned about is whether or not you're actually going to be able to put a pencil on a piece of paper and do it yourself. That's the biggest concern I have. So I'll give you an opportunity to practice a little bit, hopefully, today. And I'm going to come around. I want to see what people's writing looks like. Because that's another thing. You're sitting there like, yeah, I got it, man. It's easy, no problem. I can do this. And then you start writing. It's just like, it's like you're on 8 cups of coffee. You're just all over the place, and it just looks all crazy. And believe it or not, there is actually there's a penmanship when it comes to mathematics. My writing used to be terrible when I was in college algebra. I mean, I took no pride in my work. I didn't think it mattered as long as I got the answer. The answer right, shit, then shut up. I don't care what my writing looks like. Okay, but at some point you start to understand other people need to read it. You need to go back and read it a year later and understand it. It all has to be logical. So you have to start taking some pride in that. And it's like leaving periods off of sentences, Do you want to see people look at your writing and it's like, you don't have any punctuation. You just have sentences that run on. I mean, it's almost embarrassing at some point if your writing is that bad. You understand? Same thing with math. If you pull it out and you're like, this is my math, and people are like, oh my gosh, whoa, what is he on? You gotta get organized. So I want to see what people's writing's like. I'll come around and take a look. That sound good? It's just something to work on. Okay, I'm never going to say, okay, your writing's so bad, unless I can't read it. But I'm never going to be like taking off because it's just bad. But I'll encourage you to try and tighten it up. All right, so that's radical equations. We took a look at a couple of those. How about some quadratic form ones? We'll skip over the rational for now, and let's go to quadratic form. When it comes to quadratic form, here's essentially what we're looking for. We're looking for an equation that has some junk. Yes, that says junk. Okay, some junk, and it's squared. All right. Plus, and I'll put let's put a in front of this. A junk squared plus b times the junk again plus c equals 0. Here I'm telling you need to make your writing look a lot better, and then I'm using junk in here. I know it doesn't seem right, but the whole idea is that this is what a quadratic form equation looks like. It looks a lot like your standard quadratic. You had these, didn't you, on the assessment? Yeah. You had a few of these. Well, one at least. And they told you to make a U substitution. Remember that? Yeah. And I did that one. This is kind of revisiting that because there are a few others I want to make sure everyone's comfortable with. So this is what a quadratic form equation looks like. We can look at it as 3 pieces, right? 3 terms. Then you've got, if you put them kind of like in order, highest power down, then whatever's here has to appear here squared in order for this to work. So let's look at something semi-simple. So I put this up here. Make sure you have 3 terms and it looks like a quadratic. Make a U substitution, solve the quadratic, back substitute, and solve. So here, let's do this one. Let's do 3x to the 4th equals 2x squared plus 1. Okay, so you want to make it all equal to 0? So it's not a linear equation, right?
No.
It's not really quadratic if you're thinking squared. It's the highest power is 4, so it's not really quadratic, but you're kind of hoping it's going to be quadratic form.
Similarly, yes.
Yeah, and it's not radical, right? It's not a radical equation. So let's move everything to one side. Set it equal to 0 like that. And then if it's going to be quadratic form, we have to have three terms, which we do. And we've got to have some junk in there. So what would the junk have to be here? X squared, right? X squared is the junk. And for this to work, x to the 4th has to be that squared, is it?
Yes.
X to the 4th is x squared squared? Yes, so this should work. So what I could do is I could rewrite the problem like this. There's my junk squared minus 2 times the junk minus 1 equals 0. So all I've done is rewritten the problem, right? X to the 4th I've rewritten as x squared squared, which I'm going to do on the next step. I'm going to substitute right now. I just want everyone to see it, though. Does everyone see what I'm going to replace, right? I'm going to replace x squared with u, and then rewrite the whole problem. So I come in here. I get what I like to refer to as the God complex. You know, I just let it be. Let u be x squared. I have control over that. There, let it be, right? I'm going to replace all x squareds with u. Why? Because I'm in charge, right? You're in control of this equation, all right? There it is. Rewrite everything in terms of u. 3u squared minus 2u minus 1. Are we comfortable with this? Any hesitation, question, comment? All right. Now you're at a quadratic equation. Important thing is that you're in a quadratic equation. Let me write it down so you can see it, because when I say it, it doesn't come out as well. This right here is a quadratic equation in U. It's a quadratic equation in U, meaning that the variable is U. So anytime you're talking about quadratic equations, we've always used x in the past, right? So I've never had to tell you, hey, this is a quadratic equation in x. X is the variable. This is a quadratic equation in U. Is this a quadratic equation in x?
Yes.
Yes.
Is this a quadratic equation in x? No. This is a 4th degree equation, right? This is a degree 4, right? This quadratic is degree 2. This is not a quadratic equation in x. This is a quadratic equation in U, yes? But that is not a quadratic equation in x. So what we did is we took an equation that was not quadratic, but it has the form of a quadratic if you make this substitution. Understand? All right, so now solve that in terms of, for the variable u. So does it factor?
Yeah. It's 3u plus 1.
3u plus 1,
U minus 1.
u minus 1. We talked last time and the time before that how important it is for you to be able to factor in this class. We tried to scare you that if you couldn't factor, it's dangerous for you to be here. Okay, what are my solutions here? Negative 1/3. U is 1. Are y'all okay with that? Set each one of those equal to 0. Move things around. And that's it. Box them up. We're done? No?
You have to put the x back in.
Yeah, this you've solved for u, haven't you?
Yes.
But you were the one who came in with u, didn't you?
Yes.
Didn't we? So do you understand how ridiculous it would be for us to box those answers?
Yes.
It's like I'm asking you a question about x and you're telling me the answer is in terms of u.
And you're like,
And I'm like, what the hell's u? You know, I didn't even ask you about u. It's like me asking you for you your favorite, you know, say, what's your favorite color? And you're like, I like Doberman Pinschers. I mean, I just love Doberman Pinschers. What's wrong with you, man? What's x? Oh, we'll use 2. What? You know, it doesn't make any sense. You're not there yet. right? You got to go back. Resubstitute. So you can just replace x with, or u with what? X squared. What was the substitution we made? It was u is x squared, right? And same thing here. And now you have two little miniature quadratic equations, don't you? Now these quadratic equations can be solved a little different than we did before. We don't necessarily have to bring this number over, do we?
No.
We don't have to bring this one over because you can just take square root on both sides, couldn't you? All right, so I'm going to take the square root on the left side here, and I'm going to take the square root on the right side. What do you always have to include when you take the square root on both sides of an equation? When you come in and you physically take the square root on both sides of an equation, you must always look at what?
The index?
We're assuming that's a 2.
Plus or minus. Plus or minus. Don't forget this. The wing comes off the airplane, starts tumbling with 230 people on board because someone forgot plus or minus? No? Look, plus or minus is a big deal, right? Anytime you do this, look, if I tell you this is true, what are the possible answers to that? What can I square and get 4? 2 squared or negative 2 squared, right?
Right.
So if I go and tell you to solve for this now, you would take square root on both sides, right? If you forget to do plus or minus, then you're going to get x is equal to 2. And although I agree that is true, it is not all the answers. It's one solution. The only way to get both solutions is if you remembered that anytime you take the square root, you have to include plus or minus. It's the only way you would have remembered to get this. So don't forget that, right? That's what I'm going to do on both of these. Square root of x squared equals plus or minus root 1. So tell me about this one over here.
Oh, that's a negative.
It's a negative underneath the radical.
You don't like that.
We don't like that? Can't take the square root of a negative number?
Because that's a
Is that hands off right now? We don't touch that? No. We will, okay? We will investigate that further. Just not yet. All right? We will actually have a way of dealing with this.
And that with the imaginary number.
That'll have to do with imaginary numbers. Yep.
So right now.
Right now, no solution here.
no solution.
Yep. No solution from this part. I'm just going to put solution that's a short for solution there. And then x equals over here, plus or minus 1, right? Plus or minus 1.
So that's the only thing we have.
Two answers, right? Two answers.
One of those solutions.
Do we have to check these answers?
Yes.
Well, did we square both sides of the equation ever? We never squared both sides, did we?
So both solutions are correct.
So that's okay. That should work. There are two answers, 1 and negative 1. So let's take a look at a slight variant of this one. Okay. Okay, we can do that one. How about x to the 6th minus 7x cubed minus 8? I think I'll work a little faster through this one. This one is pretty straightforward. That is not a quadratic in x, but it is a quadratic form equation. I've got 3 terms, right? It looks like if I take the x cubed to be my u, that x to the 6th is x cubed squared, right? X cubed squared is x to the 6th. So x cubed squared, that's x to the 6 minus 7x cubed minus 8 equals 0. So I'll make my substitution that u is what? X cubed. And rewrite the problem. What will it be? U squared minus 7u minus 8 equals 0. I remember when I did this problem in the first day or whatever it was, and I think it was you were telling me you were already doing it. You weren't doing the substitution, right?
Yeah.
And that's fine if you're doing that. That's okay. But just be aware of the technique of substitution, because it is useful.
I mean, I never used the U thing, but now I see how it's.
You see how it would be, especially later on in calculus. You actually have, in Cal 2, you have a technique that we use for solving problems, and it's actually called U substitution. And it's all about replacing. What we do is we take a very complicated problem, and we look at these little pieces in there, and we identify a pattern. We say, you know what, I'm going to substitute that part out, and it's going to make the problem a lot easier to deal with. So it's a common thing, and then you substitute back at the end. Yeah.
Does it have to be U? Can it be any
No, we actually turn out running out of letters. So like we use U, and then we realize, oh, wait a minute, I need to do another substitution, and then we use like V, and then, but you can use any letter you want. But the first time students learn about substitution, they usually use the variable U. And that way everyone's just like, oh, it's U substitution. But it could be W substitution or J substitution. But you find later on that math, we save letters for certain things. You know, it just depends on what you're dealing with. Okay, I was talking, everyone else was finishing, right? This was this. And then U is 8, U is -1. So now switch it back. X cubed is 8. X cubed is -1. Careful on that. Yeah, so let's talk about this. On the last problem, we took the square root on both sides, didn't we? This time we have to do the cube root. Does anyone have a question on what I've done up to this point? So when I do the cube root on both sides, let me ask you this first. Do I have to do plus or minus?
No,
No, not on cube root.
because
In
you're gonna have the same thing.
That's right. You don't have that same thing happening with the negative is positive. So look, if you take the square root on both sides, or the fourth root, or the sixth root, or any even root on both sides, you have to do plus or minus. If you do an odd root on both sides, you do not. So this is just cube root of 8. Over here, cube root of x cubed, and then cube root of -1. What is the cube root of 8? 2. So you get x is 2, is one answer. And the cube root of -1.
No, you get,
Imaginary. Wait, no?
no, you get X.
Cube root.
Odd number.
You get 2.
What number, look, what does the cube root of -1 mean? What number times itself 3 times is -1? -1 times -1 times -1, right? What, you all said the cube root of 8 was 2, right? That's because 2 times 2 times 2 is 8? Well, the cube root of -1 is -1 because -1 times -1 times -1 is -1.
So that actually works.
So you actually do have an answer for that. Maybe we just do a quick little review. What's the cube root of -8? Cube root of -8. That'd be -2, right? The cube root of -27, -3,
That's the good one.
right? So you could keep going, right?
Right.
Next one would be 64. Cube root of -64 would be -4. And of course, if all of these were positive, then it would be +2, +3, +4.
So basically, in a nutshell, when it's a cube and it's negative, it'll stay negative.
It'll stay negative. In fact, if it's a fifth root of a negative, it'll stay negative. If it's a seventh root of an...
Pretty much any odd
No,
number.
any odd root, yes. Any odd root of a negative will be negative.
That's what I meant.
Yes. So the way you can do this is this. If you take the odd root of a negative number, okay, that's a negative number in there, your answer is going to be negative. If you take the odd root of a positive number, the answer is going to be positive. If you take the even root, right, of a positive number, the answer is going to be positive. And if you take the even root of a negative number, that's going to get imaginary. It's going to be go into the imaginary. Imaginary numbers. Okay, so here's one I wanted to show you to see how you do on this one. Okay, so you ready to do your own work? I have not given you one exactly like this. So this is a good example of how you want to take what we've done and you want to see if you can extend it out to a problem you haven't seen. Okay. Go ahead. You may work together, you may talk to each other, you may check with each other, but I want everyone working on this. See if you can make it happen. Those are negative exponents. I'm going to step out for just a minute, let you all work.